today we're going to look at mechanisms, and the mechanisms in particular that we're going to look at are simple machines. By definition, a simple machine is a mechanism that can manipulate the amount of force needed or the distance needed to complete a task. There are 6 different types of simple machines. There's a lever, wheel and axle, pulley, inclined plane, wedge, and screw. Now these are grouped together for a specific reason. We say that there is a basic simple machine, which is a lever. The wheel and axle and the pulley are just a variational lever in a different format. Then we also have the inclined plane, which is another basic simple machine. And then the wedge and screw are variations of the inclined plane, just in a different format. Now, one of the first things that we need to look at is mechanical advantage. The definition of mechanical advantage is the ratio of magnitude of the resistance force, Fr, and the effort forces, Fe. Basically, we can think of it as the ratio of a weight over the force needed to lift the weight. That would be considered a mechanical advantage. We also can look at it as a ratio of distance traveled by the effort force versus that of the resistance force. So how far did we have to lift versus how far we needed to lift the object. The mechanical advantages are calculated ratios, and what they allow us to do is to manipulate speed, distance, force, or actual function of a system. So let's look at mechanical advantage. If we say an object has a mechanical advantage of 4 to 1, what does that mean? Basically, it means that the effort force, what is needed to lift, is 4 times less than the magnitude of the resistance force, how much something weighs. It also can be looked at as the distance traveled by the forces. So the effort force travels 4 times greater than the resistance force. So if we look at this box here, and we're going to think of it in 2 different formats, we can think of it as lifting it directly up, or we can think of putting the box on an inclined plane and lifting it, where the inclined plane is one of our simple machines. So if this box weighs 100 pounds, and we need to lift it up 1 foot, the amount of effort that would be needed to do that is going to be 100 pounds. However, if we put that same box on an inclined plane, which is our simple machine, notice that the majority of the weight of the box is being supported by the inclined plane. So if we had a mechanical advantage of 4 to 1, it means we would only have to push with 25 pounds worth of force in order to get it up to the same height as we would if we had just lifted it directly. But the disadvantage of that would be that it has to travel 4 times as far in order to lift it to the same spot. Another concept that we need to look at is work. Work, by definition, is the force applied to an object times the distance traveled by that object parallel to the force. So if this is your object and we apply the force in this direction, then the distance that we are going to measure is from point A to point B, and we call that distance D. So work then is the force, the amount of force applied, times the distance the object travels. Now, work, as we said already, is the product of the effort times the distance traveled, is going to be the same regardless of the system's mechanical advantage. Work is constant. Therefore, if we have 100 pounds and we want to lift it 1 foot, the work for that is going to be 100 times 1, or 100 foot-pounds. If we put that same 100-pound box onto an inclined plane, then push with 25 pounds, the work still has to equal 100 foot-pounds, so we would have to push it up a 4-foot plane in order for the work to be 100 foot-pounds. Okay, so let's look at mechanical advantage ratios. When we look at this, we say that 1 is the magic number. If the mechanical advantage is equal to 1, then the effort force equals the resistance force, or the distance the effort travels equals the distance the resistance travels. However, if the mechanical advantage is greater than 1, there's proportionally less effort force required to overcome the resistance force. And there's proportionally greater effort distance required to overcome the resistance force. If the mechanical advantage is less than 1, proportionally there is a greater amount of effort force required to overcome the resistance force, but at the same time there's proportionally less effort distance required to overcome the resistance. The mechanical advantage can never be less than or equal to 0. And why do you think that's true? And we'll discuss that more in class, but I want you to think about it until then. So now we're going to break it down and we're going to look at two different kinds of mechanical advantage. We say that there is the ideal mechanical advantage. Remember, the mechanical advantage is the distance the effort travels over the distance the resistance travels. We call that the ideal mechanical advantage. It is theory-based calculation. Friction loss is not taken into consideration. The ratio of the distance traveled by effort and the ratio that the distance force travels are what is calculated. And it's used in efficiency and safety factor design calculations. So the ideal mechanical advantage is going to equal the distance the effort travels over the distance the resistance traveled. The actual mechanical advantage is an inquiry-based calculation, and we're going to say that's equal to the force of the resistance over the force of the effort. Friction losses in this case are taken into consideration, and once again it is used in efficiency calculations. It is the ratio of the force magnitudes. So a real-world mechanical advantage. If you look at a forklift has a mechanical advantage greater than 1. The weight machines, on the other hand, have a mechanical advantage of less than 1. It takes quite a bit more effort to lift the weight than the actual weight itself. So let's look now at our first of 6 simple machines, the lever. By definition, a lever is a rigid bar. It pivots about a fulcrum, that's the triangle in these 3 diagrams, and it pivots when a resistance force or load is applied at one point, and an effort force is applied at another point. And there's 3 different types of lever, all depending on the location of the fulcrum in relation to the effort force and the resistance force. And so we're going to look at each of these separately. In a first-class lever, the fulcrum is located between the effort and resistance forces. The effort and resistance forces are applied to the lever arm in the same direction. Notice in this example, both the forces are applied in the downward direction. This type of lever, first-class lever, is the only lever that has a mechanical advantage that may be considered greater than 1 or less than 1. So if the fulcrum is closer to the effort, the mechanical advantage is going to be less than 1. If the fulcrum is closer to the resistance, the mechanical advantage is greater than 1. In a second-class lever, a fulcrum is located at one end of the lever, and the resistance force is located between the fulcrum and the effort. So in this case, here is the fulcrum, here is the resistance force in the middle, and here's our effort force over here at the end. The resistance force and the effort force are in opposing directions. So notice the resistance force acts down and the effort force acts up. In a second class lever, the mechanical advantage is always going to be greater than 1. An example of a system that has that is a second class lever would be a wheelbarrow. If you think about it, here would be the wheel right at the fulcrum. You put the load in the container, and then you lift at the handles. So that would be where the effort is applied. In a third class lever, the fulcrum is still located at one end of the lever, but the effort force is the one that's located in the middle between the fulcrum and the resistance. The resistance force and the effort force are in opposing directions, and it's not critical which one goes up and which one goes down. It's just that they're going to be in opposite directions, and it will always have a mechanical advantage of less than 1. Now, if you think about this, we need to look at another concept. We need to look at the concept of moment. And the moment is the turning of effect of a force about a point equal to the magnitude of the force times the perpendicular distance from the point to the line of action. So if you look at this simple machine here, this lever, we're going to have, here we have a resistance force pushing down. Well, if you think about it, if you think about this being the pivot point, it means that we're going to be rotating about this point. So as the resistance force pushes down, it's going to be wanting to cause us to rotate in a clockwise manner. The effort force is what is applied to keep this from moving, and the effort force will cause us to want to rotate in a counterclockwise manner. So the moment, which is the turning effect, is equal to the distance. So this would be the distance from the fulcrum to the resistance force times the resistance force, or it would be the distance from the fulcrum to the effort force times the magnitude of the effort force. Torque is another way of thinking about moment, and it's a force that produces or tends to produce a rotation or torsion. Now, if you look at the lever moment calculations, when the effort and resistant moments are equal, we say that the lever is in static equilibrium. That means that the moments, when the moments are equal, the lever doesn't have a tendency to rotate. We call this static equilibrium, and by definition, it's a condition where there's no net external forces acting upon a particle or rigid body, and the body remains at rest. So let's look at this example here. Here we have a first-class lever. We have a resistance force of 36 pounds, and we have an effort force of 15 pounds located 5.5 inches away from the fulcrum. So using what we know regarding static equilibrium, let's calculate the unknown distance from the fulcrum to the resistance force, so this dr right here. Now remember, static equilibrium, if that is the case, the moments are going to be equal to each other so that we don't have any rotation at all. So if we look at the effort moment, it's going to be 15. Let's bring this down here, and we will change our pen so that we can actually look at this. So we have 15 pounds times 5.5 inches. That's going to be the effort moment, and that's going to equal 36 pounds times the distance away the resistance is from the fulcrum. So we'll call that dr. So 15 times 5.5 is equal to 82.5, and that's going to equal to 36 times dr. So dividing through, we end up with dr is going to equal 82.5 divided by 36. Okay. This is approximately 2.29. Right? So that means that if this is going to be maintaining balance, then the fulcrum is only 2.29 inches away from the resistance force. Okay, so now let's look at the lever ideal mechanical advantage. We said that the lever ideal mechanical advantage is equal to dE, which is the distance away from the effort, times d divided by dr, which is the distance away from the resistance. So if you think of this in terms of being pivoting around, where the pivot point is the fulcrum, the effort will cause a rotation in the counterclockwise direction, and in the resistance, if it's unopposed, will cause us to rotate in a clockwise fashion. But if you think about it, both of these are going to be traveling around in a circle. So the effort and resistance forces will travel in a circle if they're unopposed. Now, the actual mechanical advantage, this is something we actually measure. So if we set up a system and had a 16-pound effort force 5.5 inches away from the fulcrum, and the resistance force was actually 32 pounds, that was 2.25 inches away, the actual mechanical advantage is just going to be the resistance force divided by the effort force. So this is something that you measure. It's not something that you calculate. You measure by creating a system, and you put a weight on that weighs 32 pounds, and you see the actual amount of force that you need to support that weight based on a distance of 5.5 inches away. So looking at the actual mechanical advantage, we're going to say that that's equal to 32, which is the resistance force, divided by 16, which is the effort force. Okay, so the actual mechanical advantage then is going to be 2. Now the ideal mechanical advantage, remember we said that was equal to dE over dr. So that's going to equal dE, the distance from the effort to the fulcrum is 5.5, and dr is 2.25. Okay. So the ideal mechanical advantage is going to equal 5.5 divided by 2.25 is 2.44. Notice the actual mechanical advantage and the ideal mechanical advantage are different. Okay? Now, the reason this is true is because that we have to take into consideration that the ideal mechanical advantage doesn't take into consideration frictional forces, whereas the actual mechanical advantage does. So when we look at the two compared together, we're going to look at the efficiency of our simple machine. The efficiency is the ratio of the actual mechanical advantage to the ideal mechanical advantage. So if we want to know what the percent efficiency is, we take the ratios and then divide them by each other, and that's going to give you a decimal. So we're going to multiply that by 100 to get the percent. So if we want to look at the efficiency of the lever from the previous slide, remember this is the lever that we had. We had our ideal, we measured at 2.44 based on the distances, and the actual was came to a value of 2 based on the weights that we ended up using on this. So the actual mechanical advantage of 2 and the ideal mechanical advantage of 2.44. So we say the percent efficiency then is going to equal 2 divided by 2.44 times 100, and that's going to equal 82. So it's basically 82% efficient. Right, and that you would that's actually really, really good. There's some simple machines that are much more efficient than others. Levers are one that actually has a tendency to be fairly efficient. Screws, on the other hand, tend a tendency to be very inefficient. Now, if you think about this, if you look at the efficiency, you're never going to have a simple machine that is going to have an efficiency of 100%. And that will conclude our lesson on levers. We will continue with our next simple machine on the next video.